Okay, we are now in the hypergeometric distribution. Okay, the last random variable and the last special discrete distribution covered in statistics and engineering statistics course. Okay, so you can refer to statistics for engineers textbook if you do have that textbook on pages 26 to 27. Okay, when I survey on the other group, it seems that they have a problem with hypergeometric. Okay, to understand the hypergeometric, the most hardest, according to them. Okay, the most problematic distribution for them to understand. They find this distribution the hardest to understand. So please pay your attention on this particular distribution. But after sometimes, you will find that this distribution is actually the easiest. And from my experience in the past, whenever we give students this problem, this distribution in assessment, they always can score very well on this particular distribution. So maybe if you listen at first, you may find it hard to understand, but after sometimes, you may feel like this is the easiest distribution that you can grab. Okay, let's look at what we have here for hypergeometric. So the learning objectives are similar to other random variables. When you learn other variables, you should be able to identify the properties, write down the distributions, and the probability function for this particular random variable. You should be able to calculate the probability related to this hypergeometric random variable. And then, of course, you need to be able to obtain the expected value and variance, okay, based on the given formula available in the statistical table booklet. And finally, you should be able to recognize this hypergeometric random variable from real applications or practical problems. Okay. So what are the properties? It has to be discrete, yes. So you can imagine the values for hypergeometric random variable must be countable and then distinct, separate. Okay. You can list down one by one, okay, the values of this random variable, and then this is the keyword when you do selection without replacement. Okay. Actually, the major keyword here is the selection. When you do selection, okay, we will see how you do this. And then again, like binomial or negative binomial or geometric distribution, you have trial. Okay. So in each trial, you have either success or failure. Two possible outcomes only. Okay. In Poisson, we don't have trial, but we have occurrences. Okay. But in this hypergeometric, you could have trial. Some students confuse between binomial and hypergeometric. Okay. So you need to be careful with this. The difference between hypergeometric and binomial is that in binomial you don't do the selection. Okay, you have fixed number of trials, that's it, and then you observe how many successes if you define x to be the number of successes, or how many failures if you define x to be the number of failures in unfixed trials. Whereas this one, you have the number of trial, yes, but you select. You don't look at the whole trials available. You do the selection. Okay? And your random variable will define the success or failure in that particular sample and selected from the whole population. So you have the word selection. Okay? So if we define x to be the number of successes in a sample, so you have a sample here. It has to be a smaller subpopulation. Okay, you should have a selection here. So we call that as a sample of size n. So X is coming from this sample of size n, selected from a population of size capital N, which has K successors. Okay, so K successors are actually the subpopulation that you derive X. How to say? For example, very simple example. Suppose I am talking about your class as my population. Your class contains about 65 students, say. So capital N is 65. Okay,
Negative
capital N
binomial.
is 65. And then I want to select only 10 of you. 10 of you only. So 10 is small n. Okay, I should write like this. So capital N, in your example, capital N is 65. Okay, and I want to select only 10 of you. So my n, small n, is 10. 10. Okay, only 10. Okay, and from capital N, 65, I could have uh, around 40 students who are males. So my K, supposedly K is 45. Okay, so K is 45 males. If I define X to be the number of males, okay, here success or failure, those are generic. Okay, but you have to choose one of them. Okay, so you talk about, say, in the class you have male or female, two possible outcomes. So you are focusing on the number of males. Student selected, okay, in the sample of 10 students just now, selected from 65. Okay, so X should be coming from here. So X will be part of N, where the bigger number is 45 for male. Okay, so X will be the number of males in a sample of 10 students selected, maybe selected for a committee, for example, from a population, which is your section, which contains 65 students, which has 45 males altogether in that particular section, in that particular population. Okay, so that is my example. Okay, so X is the number of males in a sample of 10 students selected from a population of 65 students, which has 45 male students in the section. Okay, so you have the selection here. Then, okay, then X can be said to follow a hypergeometric distribution with capital N, in your case, in my case here 65, and small sample size N, which is 10, and what's available from the population is K, 45. So you have to list down all these values. Okay? And what are the possible values of X? Okay. So we look at the probability function first. This is given in the formula booklet. It looks tedious, but it's not actually. What you have to figure out, the probability function of X equal to a particular value is simply this numerator divided by this denominator, where the denominator disregard the groupings. Meaning you don't have to worry about groups. Male or female, doesn't matter. What you know, you have to choose small n out of capital N. So in my case, I have to choose 10 out of 65. Disregard the groupings. Male or female, doesn't matter. This is the total possible number of choices. Okay, so I have capital N, choose small n. But the numerator, you have to partition. You have to divide according to the groups. You want to choose 10 just now. But that 10 can come from male and female. Okay? So your X has to be from the male group, where the male contains only 45 out of the population of 65. I want to choose X. So X is coming from K, okay, which is part of capital N. So the rest must be female lah. The rest must be female, which is capital N minus K. So if I have 45 in your group are males, so the rest 20 will be female, isn't it? So out of 20, how many will you select? If you select X, then the left over will be N minus X. That is the number of female students selected out of 10 sample size. So remember, the denominator is disregard the grouping, and the numerator you have to divide to partition the group into male and female. Okay. And what's the possible values of X? So you have this formula, but don't worry about this formula. You don't have to memorize any formula actually. It will be logic. Okay. Here for X, the maximum it will start from the maximum of 0 and n plus k minus n to a minimum of k and n. What does it mean? So for my case here, what are the possible values of X? So my X here can go from, okay, so if you put like here n is 10 tadi, just now you had 10, k is 65, and capital N, oh no, hold on, k is 45, isn't it? Not 65, okay, so k is 45, okay, the number of males in the population, and then this is your whole number of the population. So if you add this up, 10 plus 45 is 55 minus 65, you have negative 10. Okay? So the maximum value between 0 and negative 10 must be 0, isn't it? So x starts from 0. Cannot be negative 10. And it can go all the way to, so you need to choose between k and n. Which one is the smallest? So k is 45. And small n is 10. So you have to choose the minimum, which is 10. And you know if it's discrete, so you have 0, 1, 2, all the way to 10. That's how you find the possible values of x. X values cannot be more than 10. Why? Why, guys? Why x values here in my example cannot be more than 10? Any answer? Because you only choose sample of 10. That's correct. So you know the answer. Okay? So that's how you define your x values. That's why I said it's logic, isn't it? But then suppose the number of male students in the section is only 5. Okay, I put here. Suppose I have k only 5. K is 5. So here 10 plus 5, 15 minus 65, you have 50, isn't it? So still, okay, still you have from 0. What is the maximum number or maximum value of x? What do you think? What is the maximum value of x? So here k is 5 and small n is 10. And if say 10, do you think x will go to 10 as well? Then you want to choose only 5? Yeah, Ayman, Azhar, that's correct. Okay? You cannot have x up to 10 because you want to choose only Okay, what's available? What's available in the population is only 5. That's the maximum number of male available in the population. Although you have to choose 10, okay, but what's available is only 5. So X values cannot be more than 5. So the maximum here has to be 5. Okay, so you have, in this case, you have 5. So it is circumstantial. Okay, it depends on the n value, the k value, what's available, how many you want to choose, and you can think logically what possible values of x could be. Okay, so I do have an example here. Um, so if you have this kind, x hypergeometric with 25 and 10, remember you have capital N, small n, and k. Okay, so possible values of x must be the maximum n, which is 5. Okay, cannot be more than 5 because you want to choose only 5 members or 5 sample size. Okay, so the minimum value is when you consider this, and the 5 here is the minimum between k and n. So k is 10, but then n is 5, so you choose the 5. Okay. This one, similar to the second example I shared with you just now, you, although you want to choose 5 out of 20, but what is available in the population is only 3, so x can only be up to 3. So you don't have to worry about the formula actually. You can define your own values depending on this scenario. Example of hypergeometric random variables, you can have uh, the number of male students selected from a section of 70 students, which comprises of 45 males for a committee of 7 members. Okay, just now like what you had. Okay, example that I did just now. Okay, you have to know this is capital N 70, and then this is small n 45. No, this is k, isn't it? K, but your small n is 7. And you want to choose 7 out of 70, where you are focusing on the male students. So k value is 45. The other one, the number of female students. You are interested in the number of female students in a section of 20 students, which comprises only 5 female students for a committee of 7 members. Again, here you have small n is larger than what is available. So possible values of x can only be up to 5, cannot be more than 5. Okay? So X here refers to the number of selected female students in the committee or in the sample of 7, okay, where the capital N is 20. The number of defective cards selected in a sample of 25 cards. So you select only 25 from the whole lot, which contain 140 cards. So you have capital N 140, you have small n 25, okay, where out of this 140, you have only 15 cards defective. So your K here is, so if you write down the last one, you have, okay, here you have X to follow hypergeometric with capital N is 140, and your small n, the sample size is 25. You are talking about defective cuts. So how many defective cuts altogether in the population? That is 15. Okay. Sometimes we can give you confusing statement. We are talking about the number of non-defective cuts. Information give you the number of defective cuts. So in that case, you have to change. Okay. your K is not 15, your K will be 140 minus 15. If you're talking about the number of non-defective cards. Okay, so K here will relate to your X. Okay, so here your values of X go from, you don't have to worry about the formula. It has to be 0, 1, 2, and so on until, what do you think the value? The maximum value here for X? 15, that's correct. Okay, because what is available is only 15 in the whole population. So then X has to be up to 15. Okay, so that's the example. Alright, so we only have 5 minutes to go, and it seems that I don't have enough time for the working example. So what I'm going to do now is like to stop for now, but I'm going to share with you the other recorded session, okay, so that you can look at the example. Can we do that?
Yes.
Okay, so you can
Yes.
watch the recorded session anytime during your weekend, whatever, as long as you get to know how to do the working example.